Videooperator, haben Sie die Aufnahmen gestartet? 5, 4, 3, 2, 1. Hello. All right, everybody. Today we're going to talk about HoneyBotting, and this is going to be a really exciting session. We're going to just rip through a lot of crazy security stuff. What we're going to talk about today is what you have with the power of PowerShell and the power of analysis against an active attacker working against you and your infrastructure. So a little bit about me. I'm Lee Holmes. I'm an original developer on the PowerShell team, author of the PowerShell cookbook, and I'm the lead security architect of Azure Storage, Media, and Edge. So anybody here involved in client-side security, so defending any of their client systems, checking out Defender, all that kind of stuff? All right, a couple of you. Now, you might have seen something like this as you've been exploring in the past, looking through the registry keys, and you see some base 64. You've seen it from Debo, you've seen it from Carlos. You might think, what does this do? So as an enterprising admin, realizing that the power is in your hands, you Bing it, you Google it. No, when the first result of a registry search shows the Empire Stager, you know you're going to have a bad day. Anybody here, anyone here see Will Harmjoy presenting about Empire the last couple of years? All right, so this is what a deep, deep analysis of that kind of infrastructure looks like from the defensive perspective. All right, so you realize you've had a bad day, and what makes it a very bad day is that Empire is not one of those things that happens with like bots, where you just happen to be part of a botnet, and you're like, maybe they won't notice that I'm part of their botnet, and they're just going to use me for spam. Empire, you've got an operator. It's not generally automated. You've got an operator interested in your network specifically, so it's game on. Now, enterprising person, you decided to start messing around with it. So we know here that PowerShell, when you see encoded command, that's base 64, you can start to base 64 decode it. One of the things I'll point out in the middle is the script analyzer module includes an invoke formatter command. And that's amazing. It's the very, very easy pretty printer. With a couple little modifications, you can take a bunch of this malicious PowerShell, run it through invoke formatter, and like at least have some sort of idea of what might be going on. Now that's one way to do it. And you know, the funny thing is most of the security community does not realize that invoke formatter exists, and it's just like this magic thing. But another magic thing that exists is script block logging, and you've heard about it from Debo, you heard about it from Carlos. This is amazing. John Lambert, he's a very, very, very smart guy at Microsoft. If you're not following him and you're interested in security, super, super smart, you should. And the reason why I know he's so smart is because he quotes smart people. So all you got to do is take one of these things, put it into a virtual machine, run it, and you're going to see through script block logging 4104 every single thing that this thing is about to run. But maybe you're not ready for commitment. Maybe you're not ready to just fully run malware and see what it's going to do. So we've got some options. You're aware of PowerShell debugging. PowerShell has an awesome, awesome capability here to let you just slowly analyze through a script and see what it's going to do. So let's take a look at what that might look like. All right, this is nothing new to you, I'm sure, but let's start it anyways. And I'm sure you've seen everything like this before. All right, so what we've done, this is a very basic example of PowerShell debugging. I set a breakpoint on this script. I ran it. It ran through all this stuff, and now I can start to step through and check out what's happening. So I'm starting some sleep. This counter is incrementing. I can explore what the counter value is right now. I also have the ability to run one of the amazing things that I love about PowerShell debugging is that I can now use commands to interact with the debugger. So I can do something like set ps breakpoint dash script hello debug.ps1 dash line, let's say 5. Now live, the debugger recognized that I've added a new breakpoint, and then I can continue here. And now it broke inside this function. I can take a look at counter. If I wanted to, I can even change some state here. I can continue, and it outputs hello 10. So this is a basic example of PowerShell debugging. Oh no, Defender is out of date. Not a good idea. Now, so that's what you can get when you start to do some basic PowerShell debugging. So let's quit that. Now, I mentioned to you that we have, let me just clear these guys. So I mentioned to you that we have, yes. Enlarge, yes, I can. All right. So we have this is what that stager looked like. This was that example that we downloaded from Empire. This is what your client is going to run. And, I showed you an example of this thing all pretty printed. And what you can do if you wanted to here is you can put a breakpoint on this, but then you're going to get into invoke expression and it gets really complicated. But one of the things that I wanted to show you is some of the power that you have if you run into a system where you already have an instance of PowerShell running and it's running the PowerShell stager. So what I'm going to do here is run cmd, and we're going to basically fake out what that PowerShell encoded command runs. So I've got stager.ps1, and I can run, this is what everybody does. They do start, PowerShell, dash no profile, dash window style hidden, dash command, stager.ps1. What's that? It worked just fine. Oh, wait, no, it didn't work just fine. Oh, widow style, yeah, I see. Well, yeah, exactly. This is going to be gone. All right, when you see a PowerShell window appear and disappear right quick, that might be the sign that you're in trouble. And one of the reasons why you might think you're in trouble is because I'll bet you I messed something up again. Oh, God. I checked that just before this. Thanks, Defender. Okay, window style hidden. Okay, that's the flash that's not good, and this is the flash that's really not good. This is Harmjoy saying, hey, I got now control of your machine. This is a super elite security demo because I'm doing it from Kali, and I can take a look to my agents. I've got one now connected. I can now interact with this one, and I can do things like, who am I? So now with Empire, I've got an active command and control back to this client system, and it's now starting to work, and I can now do commands against that client system. Okay, so we've got that. Now, if I take a look at all the PowerShell instances, 7084 is the PowerShell instance that is now backing that Empire stager. But what I'll show you is something pretty cool, is PowerShell attached to process debugging. So I can get ps host process info, shows me all of the PowerShell processes on the machine that I can connect to, and I can oh yeah, enter ps host set. So that was 5744. Let's just double check. 7084. Okay, so now I've got the PowerShell debugger that's connected to that session that's now hosting the Empire command and control. And I can now get the run spaces, and I can debug ID1. So now I've now attached the debugger into that run space that's actively running Empire commands. So here's an example where I can now, given that I'm attached to the active run space, I can look at the actual code that the Empire stager is running inside of my process. What I can do is I can take a look at the variables inside that process, and these variables are showing the actual encryption keys that Empire is using for communication to and from its stager. I can take a look at the functions, and these are the commands that Empire uses when it's connected back to its stager. And you see here, I've got things like invoke shell command, and this is what Empire is using every time the command and control server asks the client to do anything. Now, I showed you that PowerShell debugging is awesome at attaching to commands, so let's do set a PS breakpoint on the command, invoke shell command. And I can continue. So now what's going to happen, just like I set that previous breakpoint, now whenever Empire is asking my client to run a command, I'm going to have the ability to inspect what's going to happen. So I'm back here, and I can check out the info of this agent, and maybe I'm going to check out who am I again. This one takes a little bit longer, and that's because we're now in a breakpoint. This client is now being asked to run something from the attacker, so I can check out the code. This is the function that I'm in. I can check out what command I'm being asked to run. Who am I? So I can, let's say, step through this function line by line and decide whether this is something that I want to run. What we're talking about here is completely turning the tables on what a C2 does to a client, because that client is completely under my control. So this is where the Empire C2 agent is deciding which command to run. All right, here's where it says it goes into the who am I code. This is where it's just using the get current identity. So this is what it's about to return. But what if we want to make the attacker think that they just compromised the director of the FBI? Not bad. So Empire, this attacker is just like, I just struck gold. I just attacked the director of the FBI. This is game on. Little do they know that this is an agent under like little old Lee's control at PSConf EU. So bad attackers getting fooled. So now they're pretty excited. They're just going to double check again. Now they ran who am I again, and we're about to hit this breakpoint again. So we can continue through and step through this code. Now what I'll mention here is that in the past, People are aware that malicious input can get returned from a C2 server. So in the past, Empire has had 2 RCE vulnerabilities, where if one of them was when Empire asked to download a file from a remote agent, the agent could respond with a file name that was malicious in a certain way and start to override files on the attacker's machine. So what if, rather than this output that we're about to return again, oops, let's do this one more time. Oops, what did that do? No. Okay, so what if I say output equals get content, and I continue. So this, now we're starting to take a look at the Empire's UI layer and the way that it's interacting with things. I've got a completely malicious payload that I'm going to return on this, and I'm going to continue. Let's see what they... Oh, this is not good. Take a look at Empire. So it looked like somebody ran an exploit up there, suspended Empire command and control, ran whoami, saw that they were root. Everyone in Kali runs as root. What they did here is they listed the bash history, exfiltrated that, and then they started running a paste bin, piping it into bash. So if I'm looking at this Empire agent, I'm running for the hills. I thought I just compromised FBI.gov, and they're now reaching back and compromising me, and then they come back to Empire. This is like game over. I will point out, though, this is not as bad as it looks, but the attacker does not know this. One of the big flaws that Empire has is called UI redressing. So this output that comes back from the client can contain arbitrary VT100 escape sequences. Take a look at that window title, pwned by FBI.gov. Like, you're screwed if you see this. What happens here is I was able to return arbitrary ANSI escape sequences. I could change the window title. I could paint all the output to look exactly like an Empire stager, and no one's the wiser. If you saw this on one of your command and control servers, you would burn this thing to the ground and go into farming or something like that. So as I mentioned, there have been issues in the past where PowerShell has had Empire has had RCE vulnerabilities. They've fixed them. It's all good. But this is the kind of thing that many things in terms of command and control servers are vulnerable to this kind of thing. Empire is still vulnerable to this UI redressing issue. One of the things that's really interesting is it's very hard to get compromised with Empire. It has basically not been changed in 2 years. Defender has signatures for everything. If you're getting compromised with Empire, it's time to look a little bit deeply. So this UI redressing issues and the unescaped VT100 sequences, this has been a thing in the past where H.D. Moore has done a bunch of amazing research. In the past, there used to be VT100 escape sequences that would let you do things like retrieve all the window content. Yeah. Battery, I think.
Okay. Maybe it's just that you.
Do you got another? Has done things that will let you find escape sequences that will let you, for example, retrieve all of the window content, that will let you set arbitrary contents. Not yet? Yeah, okay. That They'll let you set arbitrary contents into files. So for example, what I could have done back in that day was set the window contents to maybe overwrite the file and log that content into the etc password and start to really override some very sensitive config files. So one of the things that I started to take a look at is the VT100 implementation in Kali. Kali is like the canonical implementation of where attackers go to host all their stuff. And the good thing I will tell you is that Kali has done a great job at parsing out all of those security-sensitive VT100 escape sequences. As you saw, they did still leave up the one for changing window titles, but that's like a bit more showmanship than it really is a security concern. But the one thing you got to worry about, like, that is a small portion of the parser that Kali does in VT100. This is all in this C language, all potential vulnerability to buffer overflows, integer overflows, all kinds of memory corruption vulnerabilities. So like, how much do you trust that there are 0 security vulnerabilities in any of that? I don't. UI redressing and exposing arbitrary VT100 to attackers is a very, very dangerous thing. So that was talking a little bit through the idea of the UI layer and what might be shown to the users. But what if we start talking about the underlying communication protocols that underlies a bunch of these command and control servers? So as you start to take a look at the Empire stager, what you'll see is that this is when the agent is in Python, all stuff that comes back and forth between those agents is compressed with gzip. So Python's compress and decompress. Now the issue here is that on malicious content, compression is extremely, extremely dangerous. You can get on malicious content 1,000 to 1 compression ratios. So on 100 megabytes, if I was one of these, now I fully control this agent. If I was to respond with 100 megabytes of very, very carefully compressed content, that results in 100 gigabytes of memory usage on that attacker server. It doesn't matter if they went and spent, $1 million on a server, that thing's getting taken down by this malicious content. So that's one example specifically from Empire, but these kind of issues are rife in the whole community. One of the things that's very, very true is that Python C2 frameworks, command and control frameworks, they love JSON. Anybody here use Python? Cool. Anybody here use JSON in Python? All right. Anybody here fully made the move to Python 3.5 and 1, 2. Yeah. Everyone's still like, I'll get around to getting off 2.7 when I get around to it. So here's the thing. This is JSON being loaded from an untrusted client in Empire. This is JSON being loaded from an untrusted client in the social media C2. I literally searched GitHub and everything I could for Python C2, Aries C2, Coadic C2, GDog C2. That's a lot of JSON being loaded from untrusted clients in Python. A lot. All of it. So why do people love JSON in Python so much? The reason is that you have dictionaries, and Python does a great job, just like PowerShell has hash tables. Python does a great job of packing all of this content into dictionaries. So with a dictionary, all of that content, now you can address it by the name and the value, just like we're used to in PowerShell hash tables. So the big thing about these dictionaries is that they're based on this magical thing in computer science called the hash table. And it is one of the things that when you talk about like high topping achievements in computer science and algorithms, the hash table is amazing. It's not only very usable in terms of I can put a string in, get a string out, but it's also very fast. I can have a hash table with like 1 million items in it, and pulling out single items is just as fast as if I had an array of like one item. It's so fast. It's an amazing thing. So this is going to get a little bit crazy, I'm warning you. But this is what we're going to do here is understand a little bit more about hash table basics. So the way that hash tables work is they take strings and they send them through an algorithm that converts that to a number. Because hash tables aren't of infinite size, what backs a hash table is usually something like an array. And so what they do is they take these strings, grind them through an algorithm that converts the string into a number. That number tells you which entry in that array that they're going to sit in. Now that magical thing is called a hash function. So this is an example of taking some strings, setting them into buckets. One of the things that happens in the real world is that these magical algorithms that are generating these integers out of strings, you're going to have collisions. You're going to have situations where you have two strings that convert and create the same integer. So when you're implementing one of these things, you have to realize that at some point you're going to have two things with the same number, and that's what's called a collision, and then you have to make a strategy that addresses these collisions. So what they normally do in hash tables is they create more lists. So if you have a collision, they'll just tack it onto a list. Collisions are very, very rare, and so you just end up having these small lists of things that collided in that same bucket. Now, the one thing I'll point out, normally when you see diagrams, they show these like lists to the side, where they're new lists that contain all the collisions. What Python does is called open addressing, where they just use open buckets in that exact same array list. Just because it's interesting. And what I think is cool is that we can take a look nowadays at the source code of all this stuff. We can take a look at the source code of this is the version in C#. This is what backs the PowerShell hash table. This is the version in Python. And it's just amazing to be able to take a look at the exact implementation of a hash table and understand how they're handling collisions and how they're doing these things. One of the things that I think is amazing about being able to see this stuff in open source is it is line 227 before anything in the Python dictionary implementation is code. Everything before that is comments describing the algorithm, major design choices that have been taken. It's just amazing to read really high-level professional quality code like that. And you'll see that a lot if you take a look through, for example, the PowerShell source code, where there's some complicated things that have like mountains of comments and then like 3 lines of code just because the decisions were so impactful. Now, I mentioned here every algorithm. I talked about collisions, and they happen. They're rare. But one of the things that's happened is there are attacks where all of these algorithms, they have the best case, they have the average case, but these algorithms also have the worst case. So what happens if you have these strings and they go through this magic blender of this hash function, and what comes out the other side is a collision? What happens if 2 things collide, or 3 things, or 10 things? How does the algorithm react when you have 10 or 100 or 1,000 collisions? These are called algorithmic complexity attacks. And people have done a bunch of research in this. I remember being blown away. It was like 2003 when people started realizing that there were data structures out there that attackers could provide input to that would cause things to start to exhibit their worst case behavior. So where you thought you had something smart in, let's say, in the operating system or an intrusion detection system, but it was based on a hash table, and this hash table you could potentially cause collisions intentionally, well then all of a sudden you've got denial of service attacks against some very, very sensitive infrastructure. So it was like later in 2011 where some folks in the CCC conference demonstrated some very, very reliable attacks against some major web frameworks. So, for example, the headers in a lot of these web frameworks are given to the programmers as hash tables. So what you could do is start to communicate with these web servers using hash tables with intentional attacks. It was a very, very expensive attack. It took them a lot of time to figure out. But they were able to do it, demonstrate it. The community in the world recognized the issues of these, and so Python, since 3.2, has included mitigations against these types of collision attacks in dictionaries. But I thought it'd be interesting. That was a very, very complicated and expensive attack. I thought it'd be interesting to see, really, fresh, this is 2019, are there any more practical attacks against Python dictionaries? Remember, we're talking the 2.7, it was patched 10 years ago, this is not dropping O days. So you can actually get, as I showed, you can actually get the source code of the Python hash implementation. That magical function that takes a string, converts it to a number. So this is an example. I re-implemented it in C, just so that I could do it without having to set breakpoints in Python. This is a re-implementation of the hash function. And what you can see here is that, I hash an example string. My hash implementation exactly matches that of Python. So we're good. We're good to go and start experimenting with this one. So let's talk about how this hash function works and the way that attacks against this hash function have worked. So in the beginning, remember, this hash function is all about creating a single number that will be the output of this hash function. So in the beginning, that single number, the output is going to be called x. We assign it to 0. You see that there. The first thing this hash function does is it takes the first letter of your input and it uses the left shift operator to just take a bunch of those bits and send them kind of leftwise in that number. Then what it does is it starts to iterate over all of the characters in your string. And for each one, it multiplies it by 1,000,003. That's just a prime number that does a pretty good job of mixing all these bits throughout that number. And then it does the exclusive OR, so basically adds in the information of the character that we're currently processing. So this is the example of it processing L. One thing I'll point out here is that P++ part, that's really the only control we have over this algorithm. That's the actual value of one of our characters. Once it gets to that box in the red, it's kind of like this bit blender. That multiplying by 1,000,003 just changes everything so crazy, and we really have no control over that part of the stuff. Now, it processes E, processes the second E. And we're just stepping through this. It's just doing that little bit of math there. And at the very end, it takes our string length and adds it to the very end of that number. And when we're done, we output the hash. You see here, we've been tracking the bits all along, and this is the value, and you can see that it matches that Python hash here. So it's kind of a quick kind of run through of that algorithm. And one of the ways that the initial attacks were done was this attack called meet in the middle. So the idea of meet in the middle is we know every time we're going through this string that that number is changing all the time, right? We saw that number changing as we were heading through it. So they just created this huge hash table, and this hash table needs to be literally 4 billion big. It's a huge hash table. And they start knowing that when I got to L, this was the hash. When I got to LE, this was the hash. And they just do that for tons and tons of content. Now, if they're trying to create collisions, they know that maybe I'm going to look for the value 0, and you can reverse some of this math, not all of it, but some of it. So they start reversing some of this as well. And at some point, you hope you're going to find when I went backwards and when I went forward, I found a hash value. So then I know an entire stream that I can take from beginning to end to get a hash value of my choosing. So when I can create a bunch of strings with a hash value of my choosing, well, that lets me create hash table collisions, which lets me get into the hash table denial of service, which can take down entire services. Now, I was talking about complicated. People have tried to do this against like the 64-bit hash function, and it's like many, 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 many hours. This is days of computation to get some of this stuff. But what I realize is that this function has a couple critical errors. So this is all based essentially on multiplication. And if you multiply any number by 0, you stay at 0. If I use the exclusive OR of 0 onto 0, you get 0. So if you can find any point in this algorithm where that number ever got to 0, well, you can just keep on adding zeros and your hash isn't changing. So that's pretty cool. Like, I can take a string that's, let's say, 100 characters and generate 255 collisions against one string, and it's so fast. So this is an example of doing that. So all I literally did was brute force a bunch of ASCII strings until I found some hashes that hit 0. And this is almost in real time. This is an example of a hash string that found zeros. It finds a couple more. And this is great. So now with, let's say, a couple dozen strings, I can generate 10,000 collisions that all hash to the same value of 0. But I think there's a better way. So these are the point where it hashes to 0 and I can move. But the issue is, remember that part of the hash algorithm where that very first letter, it shifted it left by 7? That very first part, that kind of messes it up. I can't just take the content that I did and duplicate it because there's that one phase where that initial part isn't getting repeated anymore. So this is the example where I'm just adding in zeros and it keeps on getting us that hash of 0. Because I knew when I got to that 0, I could just keep on adding them in. But there is something we can do. I was kind of bemoaning that we couldn't just copy and paste these sequences to generate arbitrary collisions, but I can. I talked about that area in the green being stuff that we can control with our characters, and this stuff, that initial stage where I shift that initial character over by 7 brings it into that bit blender where everything kind of gets messed up and I have no more control. That number is 7. That number 7, there is exactly one number when you shift it left by 7 doesn't enter the bit blender. The number 1, if that's your initial letter of your hash, if you shift it over by 7, it never enters the bit blender. So now what you can do is you can do all of the algorithm that you used to before. Once it hits that 0, that magical 0 again, well, I know that I can control that last 0. So what I did is I ran that brute forcing again, and I looked for things that started with the value 1, and then at some point got to 0. Because once that happened, here's an example. It gets to 0, but that left shifted is just the hex value 80. So this is where I can now put in that hex value 80 and get back that 1 that had happened when I did that initial shift. And I can just copy and paste now. So when I take some patterns, if I just separate them by this magical OX80 to reproduce that initial value, then I can just start to copy and paste these things and generate them. So here's like 16 patterns that I brute forced and I found. So with 16 patterns, if I take one of them, I've got 16 ways that I can generate a collision against a hash table. If I do 2 times, it becomes 256 collisions. If all I take is 8 of these combinations, I've got 4 billion collisions in a hash table. 4 billion. That takes a hash table, and this is literally as fast as once you've figured out these patterns, this is literally as fast as your computer can generate them. And this is what it looks like in practice. So initially, they're pretty close. This is Python on the left running where it's just the regular hash table performance. And on the right, this is the hash table running with collisions. And I've got 4 billion of these things in my back pocket. And you can already see, once I get to 10,000, Python is starting to crawl. The CPU is maxed out. It's spending all of its time reallocating memory. 12,000. The left one is just churning along. Using this attack with just like 100 megabytes of JSON with all of this intentional collisions, you can completely destroy anything that is parsing JSON from untrusted content. And that's just the start. This is what it looks like when you start to take a look at the time per key in a Python hash table. And remember, this is Python 2.7. This was fixed 10 years ago. So this is not dropping O days. This is just making something orders of magnitude more efficient than it ever has been. So you can see here that this gets exponential. At 50,000 keys in a hash table, you're already like sitting on your hands. When you start to get up to 100,000, like you might as well walk away. So, the point is, like, this is not ODing anything. This is not, everybody who cares about security has moved to Python 3.2 and above, where they fixed all this stuff, right? No. You try to run Empire with a version that's not vulnerable to this, and it doesn't even run. Empire does not run in Python 3.6. So there are 0 Empire command and control servers out there that are not vulnerable to a trivial JSON denial of service against their endpoints. Like that's a crazy, crazy attack against the communication protocols. And things start to get really interesting when you start to talk about the platform weaknesses themselves. So, Empire builds on Python for sure, but it also builds on some other things. So anybody ever used Python and noticed this beginning part? You set up a listener, and it's WSCGI, and it says, don't use this in production. So it's built on this thing called Flask. Now, we're going to run a second here. Like, find the massive security vulnerability on their homepage. It's 3 lines of code. Yeah, it doesn't appear that there is one, but there is one. So let's talk about, I started wanting to investigate, are there any vulnerabilities in Flask itself? And let's just find out. So one of the first things you want to do with Flask is just a simple HTTP server, and this is what Empire uses for all of its connectivity. When we're doing this initial post back to Empire, that's going through Flask. So here's an example of what you might want to first do if you're wanting to see what Flask is like in terms of being able to handle just somebody being stupid. So I was getting ready to do some amazing research on this. And so what I tried at first was I'm just going to open connections to this Flask server. Oops. And I'm just not going to close them. So what happens when you do that? So I've just now, very simple PowerShell, connecting to this Empire stager, completely pwned. And this thing is now listening. I might be checking out the agents. Might be checking out the listeners. Oh, I got that break. Yeah. So, let's see, back. Oh. That's what I get for pausing the screen. All right, this is going. And all I'm doing is creating agents. And this is, I can run, let's say top, see what's going on. Now, at some point, Empire starts having issues. I might not be happy about this. As an attacker, I might be trying to Control-C my way out of this. It doesn't work. I don't see anything here. I might start to run some commands. And my entire operating system right now is completely owned. I cannot, as a listener, on this command and control server, I cannot receive any new connections from compromised agents. I cannot see who's connected to this system. I cannot do anything. I can't restart this. I cannot start new processes. And this is from one little simple PowerShell script running on one simple laptop in a virtual machine. This is not an expensive attack against Flask. So do you see the vulnerability? The vulnerability is running Flask in production. And here's the thing, they say not to do this. People have pointed out denial of service vulnerabilities against Flask in the past, and they say, we're never going to fix one of these things. Because by putting in production quality things like denial of service protection, then what you're going to do is you're going to start to run this slippery slope, and it's not a production web server. Use production web servers for production. So this is another example. Flask takes any JSON you do it, even if you're not using JSON, and it's putting this into this request object, even if you don't use it. So not only should you not use it in production, but it's parsing untrusted JSON whether you ask for it or not. So hopefully no one's using Flask in production, right? Empire does. There's been some great research out there of identifying Empire listeners on the public internet. Tenable did some great research here using Shodan and things like that. When they did this research, they were finding like 300 in the wild. This was an example, like today you look and there's a couple dozen up just listening, waiting for somebody to connect. So with one laptop, with one VM anywhere, you can literally take down every single Empire listener on the entire internet just with a couple simple PowerShell commands. Completely vulnerable. I'm not saying to do this, but I'm not saying don't do this. So, we could be doing this right now. You never know. But we've been talking all this time about up and down the attack surface and the tracks. Now, the title of this talk is HoneyBotting. HoneyBotting has been a very well-researched area in kind of attack and defense. But what hasn't happened is the idea of how, like, HoneyBotting is the idea of an attacker connects to a server that you control. But the idea of HoneyBotting is pretty amazing. What happens if instead you've got a client that you control, and you can use that client to start to extract information about what the attacker is attempting on your machines. So the first way you might want to do this, and the core of all this is PowerShell debugging. It really is. The big issue as you start to try to tame the Empire stager, sure, you can set a breakpoint on the very last line, but ultimately all that code goes into IEX or invoke expression, and this is a core PowerShell command, and you can't debug into PowerShell commands. But what you can do is I can tame invoke expression. If it's a client that I control, well, I can just create a new function called invoke expression. So when this Empire C2 is trying to call invoke expression, it can call my invoke expression. I can have my invoke expression write that content to a file instead and launch the content from that log file. On those files, I can investigate the content. I can decide whether I still want to run them or not. I can put breakpoints in them. Once they're in files, you can start to do some amazing things. What if I do dynamic content modification? So I'm calling all of this stuff dynamic debugging, and I haven't seen any other language that's got the kind of power and capability that PowerShell has here. So what I could say here is script number 1, the first script that comes back from Empire, I'm going to replace the input with content of my choosing. So I've done this successfully in the past. To Empire, what it'll do is try to disable AMC, disable script block logging. I can decide that's not my game. I can remove that script that's about to do that so that it still shows up in script block logs. Now, dynamic debugging is amazing. What happens if when you hit a breakpoint, you can decide to create other breakpoints? So here's an example when I start to evaluate the first script, I can set some breakpoints. The second script, I can set some new breakpoints. This is super, super powerful. What does that look like? And we've got one last demo here. So I called this script a parisium, which is super, super lame. I didn't have a better idea for it. But that's what you get. Now, a parisium just takes these ideas and it runs any given script block under the concepts of dynamic debugging. And you do, the main part of customization here is your breakpoints and some of your content modifications here. So what if I run now? What if I run the Empire Stager under a parisium? So it's going to extract. A parisium was like Harry Potter for like make a thing appear. So what if I run this stager under an approach that now is using dynamic debugging? So I've got this stager, and now this is connected. Empire's got a new one, so I can check out my agents. Let's give this one last try. Oh, it's on a breakpoint, that's why. So what was on a breakpoint was I'm about to evaluate the Empire Stager. Do you still want to run it? So what you can see here is I can open up dynamic content, and I have the first script that I just wanted to run. So there's a breakpoint here. I can take a look. This is where Empire is about to ask the agent information back from the user. So this is telling Empire what is the information about this person about to connect. Well, I can change that. So I can maybe say this is Linux on the desktop edition. Now all I got to do here is this one last bit. And I can continue. So this agent now has checked in, and this is AFV. Now you can see I'm able to lie, kind of like we did, and I could have done this thing completely in script, where now Empire thinks it has found this new Linux on the desktop edition. Now this is pretty gold. I can say, who am I? This is my favorite command. And I'm asked to run some things. I'm just going to continue this time. And this is where I've been able to do some dynamic content. Did you know you could do ANSI art in Who Am I? So we have taken a big old path through the Empire's user interface. We've taken a big journey through the dependencies that it takes on JSON, Python, old versions of Python, Flask, and finally culminated in a dynamic debugging framework that you can use to extract confessions from any client-side impact, any client-side implant. And this whole time, I can now open up my logs file. My dynamic debugging has been capturing all of this stuff in a logs directory. And from here, I can do this at scale and start to do broad HoneyBotting against people trying to attack our infrastructure. These are our systems. These are under our control. These are under our turf. And we have the power of PowerShell and dynamic debugging to completely bend them to our will. Thank you. We have 5 minutes for questions, and then we can take any further ones out for coffee. Anybody have any questions? How do I deploy Flask in production? What? All right, thanks everybody for your time.
Yeah, Lee, sorry.
Oh, no, I had a question. What?
From a defense point of view, would it be a good idea just to grab all maybe Empire commands and just set a breakpoint to them? Because if I don't commit the breakpoint, it will just never return anything.
So the question was, is it possible to put a breakpoint on all Empire commands to have it not return anything? And is that what your question was? Yeah, absolutely. Like, this is under your complete control. You could decide, by the point you've got this under dynamic debugging, you could decide that you're going to fake out all the responses. You could make it just never return responses. You could decide, like, I'm just not going to play this game and shut down that PowerShell. Like, anything you can imagine, you can do, because it's completely under your control. Any other questions? Cool. Thanks, everybody.